So let's look at an example of how we can use those with a parametrically defined curve. So this is an example out of your book. We have this curve that's defined parametrically, x equals t squared minus 5, y equals 2 sine of t, and we're on the interval from 0 to pi. So t is on the interval from 0 to pi. And we want to do three things. We want to sketch a graph of what it looks like, including its direction. So when we have a parametric curve, unlike a rectangular defined curve, it's going to have a direction because it starts at some point when t equals 0 and it ends at some other point when t equals pi. So we're going to sketch it. We're going to find the highest point on the curve. So this is an optimization problem. We want to figure out what the maximum y value is going to be. And then we want to find any points of inflection. And to find points of inflection, what are we going to have to do? Take the second derivative. So to start with, let's sketch this graph, but let's use our calculators to do it. So I want you to grab your calculator, plug that in, and see if you can get a graph for this function, or this set of functions. All right, so I've created a coordinate plane here that I scaled the way I think it's going to need to be. So what I did is I just plugged in t values. If x starts at 0, that means this is going to be negative 5, right? So my x values are going to be going from negative 5 to whatever pi squared minus 5 is. Pi squared is around 10. It's a little bit less than 10. So pi squared minus 5 is going to be a little bit less than 5. So I scaled my x-axis from negative 5 to 5. Along the y-axis, I know that from 0 to pi, sine is always going to be positive, and it's going to go from 0 to 1. So this is going to go from 0 to 2. So my limits on my window should be approximately those values. And then what does the graph end up looking like? Yeah, so it actually kind of looks like an airplane foil, right? So it kind of goes up quickly and then something like that. Do you agree? I maybe put a little more curve in here than it should have been. I don't know if I graphed this exactly right, but it's something like that. So we can see the maximum value is going to be somewhere over here in the negative x values. And this is pretty straight right here. But if we're looking for a point of inflection for the third part, we can see this is concave down here. The only place where the concavity might change is somewhere over here. So just kind of thinking ahead, we're going to be looking for a maximum value around here somewhere. We're going to be looking for an inflection point around here somewhere. So the second part says find the highest point on the curve. The highest point is talking about which axis? The x-axis or the y-axis? The y-axis. So we're looking to maximize the y value. So how could I maximize the y value? So we need to take the derivative. We want to maximize y, so we're going to take the derivative of y. So we find dy dt, and dy dt is going to equal, did you say 2 cosine of t? Okay. So dy dt is going to be 2 cosine of t, and then we want to set that equal to 0 to find critical points. Notice that this doesn't have anything to do with the x function here, the x parameter. It only has to do with the y. So we set that equal to 0. Remember, t is on the interval from 0 to pi. So let's think about what's going on here. At 0, what is cosine going to be? 1. At pi, what is cosine going to be? Negative 1. So at some point, cosine is going to be equal to 0. Where is cosine equal to 0 on that interval? Okay, so cosine of t is equal to 0 at t equals pi over 2. Now, how could we justify that that's going to be a maximum? We always want to justify things, right?
Can't be minimal because the limit is from...
If I use a sign chart here on dy dt, that's going to allow us to use the first derivative test. And so from 0 to pi over 2, is the first derivative positive or negative? Is cosine positive or negative from 0 to pi over 2? That's positive. So it's going to be positive here, and then to the right of pi over 2? It's negative. So if we were going to justify this using the first derivative test, what do I need to say? Since what's positive? Since the first derivative, since dy dt is greater than 0, and let's just practice writing this out. Since dy dt is greater than 0 on this interval, we don't need to include the endpoints. And dy dt is less than 0 on the interval to the right. What does that mean? Then what? Then y is maximized at where? At t equals pi over 2. Or we could say y has a maximum at t equals pi over 2. Now, I still haven't answered the question, though. The highest point on the curve is actually going to be an ordered pair, right? So we want to find the coordinates of that point. Is pi over 2 going to be my x-coordinate or my y-coordinate? Trick question. It's neither. This just tells us when it happens. It doesn't tell us where it happens. How do I figure out where it happens? Plug it into this equation here and plug it into this equation here. So my x-coordinate, so x when t equals pi over 2 is going to equal what?
I'm sorry.
You guys agree with that? Pi squared over 4 minus 5?
Yep.
Do you know how I got that? Let's put that in terms that make more sense to us, though. Type that into your calculator and let's round that to the nearest thousandth. Negative 2.533? Is that what you said? Okay, and then y evaluated at t equals pi over 2 is going to be what? It's going to be 2 times the cosine of pi over 2. What's the cosine of pi over 2? Or, I'm sorry, sine of pi over 2. What's the sine of pi over 2? The sine of pi over 2 is 1, so this is going to be 2. And that makes sense because the greatest value of sine is going to be 1, so the greatest value of 2 times sine should be 2, right? So our ordered pair here then is going to be negative 2.533, comma 2. And that is the highest point on the curve. Now, before we go to the point of inflection, I want to talk about this real quick. We found the highest point on the curve here. We could have done the same thing to find the lowest point on the curve, right? Except to do that, we would find the minimum instead of the maximum on y. What if I asked you to find the point that's furthest to the right? Or the point that's furthest to the left? Instead of doing this with y, what would I do? Do it with x. Since I want to find the point that's furthest to the right, then I would find the maximum x value. If I want to find the point that's furthest to the left, I would find the minimum x value. So using parametric equations, not only can I find maximum and minimum y values, but I can also find maximum and minimum x values. So we would say that's the rightmost point or the leftmost point. Or it may be worded slightly differently, but that's going to be kind of the idea. So that's going to be something that you're going to be asked to do also. Not just find the maximum and minimum y value, but also find maximum and minimum x values. So now we want to find points of inflection. To find points of inflection, what are we going to need to do first? Take the second derivative. So just to refresh here, we had dy dx is equal to 2 cosine of t, right? So the second derivative, we're going to say this is y prime here. The second derivative is going to be d squared y over dx squared. That is the derivative of y prime with respect to t.
Wouldn't it be dt?
This is going to be the derivative of y prime with respect to t over what? Dx dt. Now, we don't know, I lied here. This isn't right. This is not y prime up here. So y prime is actually going to be dy dx. So to find dy dx, what else do I need?
dx dt.
I need to know what dx dt is also. So we know what dy dt is. That's going to be 2 cosine of t. I'm going to put that off in the corner here. We also need dx dt. And dx dt is going to be what?
2t.
2t. So then what is y prime going to be? Which is, y prime is going to be dy dx.
Cosine t over t.
Yeah. So it's going to be 2 cosine of t over 2t. The 2's are going to cancel. So it's going to be cosine of t over t. So this right here is the first derivative. And actually, we could have used the first derivative here to maximize this also. So if we figure out where this is at a maximum, I'm sorry, when we figure out if this is 0, changing from positive to negative, that's going to give us a maximum also, but we didn't need to do that. So what we need to do now is take the derivative of dy dx with respect to t on top here and divide it by dx dt here. So how do I take the derivative of this? What am I going to have to do? I'm going to need to use the quotient rule. So I'm going to need a little more space here. Quotient rule, low d high. What's low?
T.
D high minus high d low
Cosine t.
times 1, right? All over the derivative of what's below, t squared. Or not the derivative, sorry. The square of what's below. And that was a while ago. And then we have to divide that by dx dt. We already know what dx dt is. What is that? 2t. I can simplify this. This is a complex fraction. So what I would do is put the 2t down here with the t squared and make that what? 2t cubed. So I'm just going to do that right now. Yeah, so we need to set this equal to 0. So we need to find the critical points or the potential inflection points by setting the second derivative equal to 0. So we set that equal to 0, which means that the numerator is going to have to equal 0. So we have negative t sine of t plus cosine of t equals 0. And how do I solve that? So if we graph this, we restrict ourselves to the interval from 0 to pi. And also, since our t value is going to be an intermediate answer, we're finding points of inflection. What I would do is save my x value stored in my calculator so that I can I can plug in a number with a lot more accuracy. But we're going to get t is approximately equal to what? Okay, we get about 2.798. So in your calculator, what you can do, once you find the zeros for this, once you find that 0, you can go to your home screen and hit the store button and store it for a variable. And if you do that, I'll just put on here store for A. This notation lets me know if I'm grading your test, or lets a grader on the AP test know that you're going to put this in your calculator. And then you can use A as a variable later on. And once we do that, what would we do to show this as a point of inflection? You can actually use the graph that you got to justify that it's a point of inflection. How can we justify it's a point of inflection?
Plug in
The
numbers.
second derivative changed from,
Concave down, concave up.
well, the second derivative changed from negative to positive, which means that the function itself is changing from concave down to concave up, right? Which means that it's a point of inflection. So if I ask for a justification for something like this, you could give that. You could say that the graph of the second derivative changes from negative to positive, which means that the curve itself changes from concave down to concave up. So we get t equals 2.798 something something. That we're going to store in for A. And then to figure out the coordinates of A, we're going to put that value in for t here, and we're going to put that value in for t here. So on your home screen, if you stored it for A, you can type a squared minus 5. That's going to give you the x coordinate. And you can type in 2 times the sine of A, and that's going to give you your y coordinate. Alright, so again, if we type, once we have this stored as A in our calculator, we type a squared minus 5, we get 2.831 to the nearest thousandth. We type 2 times the sine of A, we get 0.7673. Is that right? And so our point of inflection is going to be right about there, I guess. So that turns out to be a point of inflection where it changes from concave down to concave up.